Hello, I am Mary Jiang from the Chinese University of Hong Kong. Today, I am very happy to present our work in CVPR 23, named Federated Medical Image Segmentation with Client Contribution Estimation. Our poster session is on Wednesday afternoon at 376. First, I will give a brief summary of our work. In this work, we aim to engage and motivate more clients to join FL by giving them a fair contribution estimation results. Our key idea is driven by the Shapley value, which is a classical concept in game theory. It can help to value each agent in a multiplayer game. However, due to a very high computational cost of Shapley value, we hereby propose to approximate it by measuring the contribution of each client given a certain client and all remaining other clients. Our estimation is conducted in gradient and data space. The efficacy of our method has been demonstrated with comprehensive experiments and analytical studies. Next, I will give the introduction of our work. Nowadays, with the high need of data to train a good model, the data protection becomes more and more important. Many different countries and areas have proposed their own data regulations or laws to protect the data privacy. To cope with this trend, federated learning here proposed a new way to train model without sharing data. Compared with traditional centralized learning paradigm, where each institutions may need to share the data and the model will use all the data together to train. However, in federated learning paradigm, there is no need to share data. Instead, the model parameters will be transferred or shared across clients, but the data will be kept locally. However, it is not easy to always pull all the centers together. For a new client, if it wants to join the federation, it may take some costs, and also the client itself has some concerns. First, the client may need to do the data annotation and also need to buy some new machines and set up the system to cope with the federated training. They may consider that whether they can have a fair reward or if they can have a good model, especially when their data distributions might be different from existing clients. So to address their concerns, we here propose to study two major problems related to fairness. The first one is collaboration fairness, where we aim to give a fair reward, allocation, or credit assignment to each client. The next is the performance fairness, where we want the client whose data might be less or might be different can also have a good model, which is also known as a less inferior in performance. So in other words, we want to pursue a uniform performance distribution. To do this, we first draw the insight from Shapley value calculation, which is shown in this equation. We can say to calculate the Shapley value, we need to enumerate all potential combinations. So with the increasing number of clients, this kind of cost can be exponential. So we propose how to approximate the Shapley value. If we concentrate on the equation, we can say the major point is how to evaluate a certain client given all the other possible combinations. So we propose directly compare one client and all the remaining clients, which is denoted as n minus client I or n exclude client I. Our estimation is performed in two spaces, the gradient and the data space. After the measurement, we can use the final estimation results as the aggregation width to promote the overall federated training and have a fair global model. So first, in the gradient space, we propose to calculate the gradient direction to reflect the information diversity. First, we have the aggregated gradients from all the clients, and also we propose to calculate I excluded gradient. These gradients remove the gradients from a certain client I and utilizing all remaining gradients. By calculating the cosine similarity using these two kinds of gradients, we can measure how diverse a certain client can provide information to the overall federation. Next, in the data space, we propose to measure the model error on the local validation to further complete the estimation. Similarly, we have the aggregated model and also the I excluded local model. By measuring the I excluded model on client S data, we can see whether the contribution from client I really helps minimizing the error. If so, it means client I really contributes to the federation. If not, it means by using the parameters from other clients, we can already have a low error on the client I's new data. By combining these two kinds of metrics, we complete our estimation and can deliver a good estimation results and also help promote the federated training. To evaluate our method, we use two segmentation tasks, the prostate MRI segmentation and the retinal fundus segmentation. We plot the data distribution in the bottom figure. We can see each client shares a very different data distribution, especially for the client 5 in the retinal fundus. Here, client 5, the distribution shifted a lot due to a different imaging protocol. We here present some measurement for the collaboration fairness and the performance fairness. For the collaboration fairness table, we propose to get the ground truth of each client contribution by conducting the leave one client out experiment. Then we compare the contribution estimation by using our method and all other methods. Here we calculate the three metrics between the ground truth contribution and estimated contribution using the Pearson correlation, Euclidean distance, and cosine similarity. We can see our method presents the best measurement on the client contribution. Next, we compare the performance with different methods. As shown in the bottom table, we can see our method presents a more uniform distribution, which means the standard deviation among clients being lower than others. Next, we conduct some analytical studies. The first one is the free rider detection. If a client does not have enough data, it can cheat by repeating one image for several times. However, the contribution should not be determined by the number of samples. So here, by utilizing our method, we can easily identify the free rider when the training goes on. Next is the robustness against different distributions. We here construct two different distributions by including and excluding client 5, and we can see our method can give a relative stable estimation given two different data distributions. This is the end. Thanks for your attention. If you have more questions, please feel free to put online, or we can have a discussion during our poster session.